Let's go ahead and talk about atoms. Now, as I've mentioned before, the first couple chapters that we do, there's a lot of review involved. So a lot of what I'm going to talk about right now should be a review from your previous course. So I'm not going to go into too excruciating detail because I expect that you have seen a good portion of this before. Now, one thing though that you may not have talked about in your prep class is understanding the imaging of atoms. So this is really interesting. So March of 1981, and I'm going to date myself here because I was born in 1981. So this technique is as old as I am. So we've got this STM technique where we can quote unquote see atoms. It's called scanning tunnel microscopy, but unlike a normal microscope where you look through the viewfinder and you see an image, the way STM works is you can see this little thing on the side here, this tip, where the tip goes across the surface, and every time an atom is there, it goes up, and then it goes down, and then it goes up, and it goes down. And so we can see atoms. Basically, it's kind of like, if you think about the way a blind person can read Braille by their fingers going across those bumps, it's essentially in that sort of a thing where it's going across these bumps. And so we can get all sorts of pictures of these things. So here I've got a silicon wafer and then some individual silicon atoms. Now, STM required certain things to be charged. You had to be conducting for it to work. We have developed another technique called AFM, which is atomic force microscopy, and this allows us to image things that are non-conducting. So these two images actually I got to generate when I was in graduate school. They do this neat thing when you're in a PhD program where you take this survey class that introduces you to a whole bunch of different techniques that you may or may not have gotten exposure to in your previous schooling. So it was just this really cool like survey lab thing where we got to basically play with all of the really fancy instrumentation that the university had. And so during one rotation, I got to do some AFM. It was really neat. Though if you look at these pictures, these are 1 micrometer by 1 micrometer. So these are tiny, tiny images. These things took several hours each to image. And so you can see from the little density map on the side where it shows that the lighter colors are higher up, the darker colors are lower down, and so as it went across the surface, it would do that imaging. The brown image is only brown because I colored it in post, because if it's just going across the surface, I don't actually know if that was the color of anything right up there. You can manipulate it when you're all done. But these things take forever to do because it's a very slow process of it going across. And then one thing that I have linked on Canvas is this really cool thing that IBM did called a boy and his atom, where because the STM requires things to be charged, you can actually move atoms. So if you have the tip on an atom and you charge it, you can pick the atom up and you can move it, drop it back, release the charge, and it goes to its new position. And so they did the stop motion animation of the stick figure with individual atoms, and it's really cool. So I've linked that on Canvas so that you can see what they can do with this technology. Okay? All right, now something that you should be familiar with is the law of conservation of mass. So basically, in an ordinary chemical reaction, i.e. non-nuclear, okay, so when I say ordinary chemical reaction, here what I'm referring to is non-nuclear. Okay, so nuclear reactions have their own set of rules, which if you are going on to second semester general chemistry, you will do a whole chapter on nuclear chemistry. So basically, in an ordinary reaction, mass is neither created nor destroyed. What I put in is what I should get out. When we do our experiment on the reactions of copper, if you are at the Grossmont College Chem 141 course, we do this reactions of copper, which illustrates the law of conservation of mass. You start off with a little piece of copper wire, you do a whole bunch of stuff to it, and at the end, you get solid copper back out. Now, if you think about what you have done previously in the lab, do we always get that perfect 100% yield though? I mean, we should get a perfect yield where what we put in is what we get out, but that's not always the case. Things happen during the course of an experiment. And so I may think that I'm going to get a perfect yield, but in actuality, what happens is all sorts of things. So what I want you to do is I want you to think about what you've done in the lab prior to this course. And in your notes that you're turning into me, I want you to jot down a couple of things that you can think about that might affect your yield. Is there a situation where it looks like you created mass? Did you get more than what you expected? Is there a situation where it looks like you lost mass? Did you get less than you expected? But you didn't actually create mass. You didn't actually lose mass. Something happened or multiple things happened during the course of your experiment that could cause your final result to be off. So in your notes, I want you to jot down just a couple things you can think of that may affect that. And next time we meet in the lab, we'll actually have a conversation about that. But I want you to have already thought about some of this stuff and have that in your head so that we can have a productive conversation there. Okay, so in your notes, I want to see a couple of things that you can think of that could happen that might throw your numbers off. Okay. We also have this law of constant composition. So if I have different samples of a substance, I'm always going to have the same proportion, and we're always going to have the same proportion regardless of where the compound was formed. So if I have water from my tap versus water from Lake Murray versus water from the ocean, just the water portion is always going to be H2O. There may be other stuff dissolved in the water depending on where I get my water sample from, but water itself will always be H2O. All right, we have this law of multiple proportions. Two elements combine in different ways to form different substances. We're going to get small whole number ratios of each other. And it has to be whole number ratios because can I have half of an atom? No, I can't. So I can look at these two carbon oxides. You may have seen this example in 120. I'm going to show you how this works, and you may recall something like empirical formulas. Because if I look at the masses of these out of 100 grams of compound, and I think about the molar mass of each substance on the periodic table, I can get those whole number ratios. So let's take a look. All right, so I have my first one. So my compound number 1, I had 57.1 grams of oxygen, and every 1 mole of oxygen, I have 16 grams. So I get 3.57 moles of oxygen. For carbon, I had 42.9 grams of carbon. 1 mole of carbon for every 12.01 grams of carbon gives me 3.57 moles of carbon. Okay, this should look familiar, hopefully, to empirical formulas. So I have carbon 3.57, oxygen 3.57. Again, I can't have a fraction of an atom. So to get my whole number ratio, we have to divide every atom in the formula by the lowest number of moles. These are the same, so this math is easy. Divided by 3.57, divided by 3.57. And my first carbon oxide is going to be CO. And if you remember your nomenclature, this is carbon monoxide. Okay, I can do the same thing for my second carbon oxide. Okay, my second one, I had 72.7 grams of oxygen, 1 mole for every 16 grams. All right, and then I had 27.3. Okay, and I get this 2.27. Okay, so carbon 2.27, oxygen 4.54. Again, I'm going to divide by the lowest number of moles, so The 2.27 is the lowest. And I'm going to get CO2. So that's my second carbon oxide. If you remember your nomenclature, carbon dioxide. Okay, so those are our two carbon oxides here for this example. So again, whole number ratios. Okay, now we'll go to Dalton. Now, Dalton's atomic theory had multiple pieces to it. So again, you should have seen this in your previous course, but we'll just quickly review it. For Dalton's atomic theory, we have these small indivisible particles, okay? So think about what you know, what you remember. Does this hold true? Do we have these small indivisible particles called atoms? Yeah, for the most part. I mean, now we know that, we can take a particle accelerator and we can smash things. But yes, generally speaking, matter is composed of these small indivisible particles. Dalton said that we have atoms of a given element are identical in mass and behavior. Different elements, different mass and behavior. Okay, when I combine things, I'm going to get those small whole number ratios, so that law of multiple proportions. And then when I do a non-nuclear reaction, we're only going to rearrange the way things are combined. We don't actually change the atoms themselves. If I want to change the atoms themselves, I need to do some nuclear chemistry and have access to a particle accelerator, which I do not. All right, so of these 5 things, there's one of them that, as we've learned, isn't quite completely true. Do you remember which one it is? Think about that for a second. All right, it's this one right here. Okay, atoms of a given element are identical in mass and behavior. Well, we know that atoms of a given element are identical in behavior, but we do know about isotopes. And so we know that they're not all completely identical in mass. I can have a carbon 12, I can have a carbon 13, I can have a carbon 14. So the mass differs a little bit. Okay? Now, we've discovered a lot of things. We know that, yes, we've got these atoms, but we know that there's things inside the atoms, okay? So what have we learned are inside the atoms? Well, we know that we've got our protons, our neutrons, and our electrons. All right, well, we learned about electrons from these Crookes tubes, so these cathode ray tubes. So we would have these negatively charged particles, electrons, that would flow from the cathode to the anode, the negative end to the positive end. They used this Maltese cross, and so if it was up, it blocked the flow of particles. If it was down, then the particles kept flowing, so they knew they were actual particles there. We figured out this mass to charge ratio for electrons based on this electrical setup here where there was an electrical beam, and so we could deflect the electrons, and based on the deflection, we could figure out their mass and that charge. So we got that ratio from them. There's this oil drop experiment where we figured out the actual charge, and so we would mist some stuff into there. The particles would go through. There would be this beam, and so as the particles fell, normally gravity is just going to cause them to fall. But if I have a beam in the center that is charged and I charge it the right way, I can get the particles to suspend. And so where the particles suspended is how we figured out the charge on the electron. And then because we knew the charge to mass ratio, if I know the charge and I know the charge to mass ratio, I can solve for the mass of the electron. Okay, we also were able to figure out things about radioactivity, so we credit that to Marie Curie. So Marie figured out the becquerel, which is a standard unit for radiation, and curium was named after Marie Curie. Okay, you may have remembered learning about Rutherford's gold foil experiment, where they postulated this plum pudding model of the atom, where what they expected to see was when they bombarded the gold foil with alpha particles, they expected to see most things going straight through, and then maybe a few, that's a bad drawing. Okay, well, apparently I accidentally advanced the slide when I was trying to fix that, so I'll redraw my picture here. You can sort of see some of it down here, but basically they were expecting to see okay, they were expecting to see the particle go straight through with only a few minor deflections. All right, there we go. So they expected to see, you know, a minor deflection, because what they had said was that we've got this diffuse sphere of positive charge, and then all the electrons were dropped in there like plums. All right, but what they actually saw were some major deflections, and so they knew something else was there. And that's how we figured out that the nucleus existed. The nucleus was the center where most of the mass was. And so we were able to then figure out, okay, so something's there, because we knew that there were positively charged things, we knew there were negatively charged things, so our protons and our neutrons, our protons and our electrons. And later on, we were able to figure out information about the neutrons. So the neutrons have about the same mass of a proton, and then the electrons are much, much, much smaller. For the symbols, sometimes you'll see proton with just a P, sometimes you'll see neutron with just an N, but you'll always see that electron with the negative. Okay, and so protons have an effective charge of +1, neutrons 0, and electrons with an effective charge of -1. All right, and then just to give you a visual comparison, if we think about the mass of a proton, that'd be like a baseball, and then an electron would be a grain of rice. So you can see there's a very huge difference between the two of those. All right, so hopefully that was review. You remember hearing most of this from 120, with the exception of maybe not having learned about, STM and AFM. But for the most part, this should be direct review of what you did in 120.